Hi, everybody, and welcome back to Human Systems Engineering 542, Foundations of Human Systems Engineering. Today we will be talking about controls. Controls, of course, are the things that enable you to transmit information to a system or a product, and basically they can change how the system or the device or the product works. The important thing about controls is how they're designed can affect all kinds of things: use error, task completion time, satisfaction, all kinds of things. And thankfully, we have a lot of things to play with in terms of our bag of tricks when we're designing controls. We can choose different shapes and sizes and colors and all of those kinds of things. And that helps us dial in just exactly the right controls for the particular task. You can see over to the right-hand side, I've got a little table that shows the type of information that's transmitted by different types of controls. So you'll notice I've got them divided up sort of into continuous controls and discrete controls. Over here, we can show whether the force required to actuate or activate the control is small or if it's large. And then here, whether it's discrete, that is kind of on or off, or one of two levels, or whether it's continuous, that is, does it have multiple levels that you choose from. So push buttons and keyboard buttons and toggle switches and all of those kinds of things are discrete controls. And if you think about some of the really big discrete controls, those might be things like push buttons that you use with your foot, and that's included down here. Whereas continuous controls would also be perhaps for large foot pedals and so forth, but that would be the more you press, kind of the more it goes or the more it stops. And that's what we're referring to. Of course, cursor positioning, things like joysticks and trackballs and mice and all of those kinds of things are really continuous kinds of controls. So the idea is kind of to change your way of thinking about controls as just on or off and just continuous, to really think about all of the ways we transmit information or give input to a product or a device. It's important to figure out how to help people identify both what the control is, what it's for, and also how it works. And we call that kind of thing coding. So coding, C-O-D-I-N-G, can be done by location. That is, we can separate our controls by 2.5 inches vertically and 4 inches horizontally so that selection errors don't occur. But we can kind of tell when we put a control on a device. You can tell which control it is partially by where it's located. But also different controls have different colors, different controls have different labels, all of those kinds of things. And we use all of those things to help people identify both what the control is and how it works. It's probably worth mentioning that although labels are used quite a bit, they're probably the slowest for people to kind of grasp. We have to stop and read those things. And even when it's just a short label, still reading it often takes more time than detecting its color or its shape or its location. There's some ways we tend to think about certain types of things like colors when we're talking about color coding for controls. So for example, usually with controls, we know that when we see a red button, it often means stop or reject or cancel or something similar to that. And when we see a green button, we usually think of go and start and accept and so forth. And that's really true in the US. It's largely true in other places too. Over on the right-hand side, you can see the concepts in the middle and kind of how they're perceived or identified with or associated with in both the US and in China. So you can see things like safe, and the color green is pretty darn similar in China and the US, whereas green and go is seen very strongly in the US and just somewhat strongly in China. So it just goes to show that these things aren't completely universal in terms of their color and the associations they have with it, but there is an awful lot of overlap. So let's keep talking about coding. As I mentioned, color is one way to code something. So if something's red, you think, well, that might mean stop, for example. On the other hand, we can code by size too. For example, large controls or dials, for example, should cause bigger movements. This is an example of a microscope over on the right-hand side, and you can see it kind of has two dials here. On the left-hand side, if you want to do gross movements, to sort of dial in the specimen that you're looking at, that is by moving around the outside. If you want to get to fine movements, that is dialing in this smaller component right here. And people tend to grasp that pretty easily. So that's the idea, is larger controls tend to cause bigger movements, smaller controls tend to cause smaller movements. We can also control, as we mentioned a little bit ago, by location. The best example of location coding that I can think of is just looking at the controls of an automobile. So typically the gas or the acceleration is always on the right-hand side and the brake is always on the left-hand side. You can also see that they've coded that by shape as well. That is, it's kind of vertical and long on the right-hand side and horizontal and kind of wide on the left-hand side. So that's an example of location coding, although interestingly, it also mixes in shape coding. So again, the coding is just used to help people understand what the, well, actually identify the control, and also give some idea, if possible, about how that control works. Here's another example, shape coding. So we've talked about color coding and location and things like that so far. Shape coding can be useful too. So here is an example. This is a system from Bayer, if I recall. But this is a shape that indicates, I think, boy, that's a great question. I think it indicates stop. I'm not sure, but you can see it has a very specific and somewhat rare shape for it, and I think Bayer uses that for all of these injection system devices. Here's another example of shape coding. In this particular case, we're looking at glucose meter, I believe, and shape of an arrow going up or a triangle pointing up indicates that we're increasing. The arrow going down or the triangle going down indicates that we're decreasing, and both of those are different from the OK button, which is circular. And I think we often end up, these are terrible pictures by the way, sorry, but we often end up making good use of shape coding. So these are some old data from a long time ago, but just indicate that people tend to be really good at just reaching out and grasping different shapes and so forth, and they're able to tell one from the other without even necessarily being able to look at them. Now these are some pretty funky shapes, I give you that, but it would be interesting to sort of look at what types of shapes seem to make sense for different types of interactions on a product that you're designing. The same thing can be said for texture. Again, an ugly, probably now that I think about it, from the same publication, another ugly picture on the right-hand side, but on the right-hand side you should be able to see different amounts of smoothness and coarseness, I suppose, when it comes to texture. But you could reach out and grab something without necessarily even looking at it and be able to discriminate one from the other. You want to make sure that that's not the only coding you're doing, because it's not perfect in terms of our ability to discriminate one from the other, and it may vary depending on if you're wearing gloves or things like that. You might not be able to detect those fine distinctions. And of course, this is probably the one you're familiar with, label coding. Most controls that we have a label associated with it, and that's the one we often really count on if there's some uncertainty. We'll actually read the label just to double check and make sure. And those labels should be placed in really close proximity to the control that they're controlling, or the control that they're referring to. Whenever possible, make sure that that label isn't blocked from view by the user's body or hands or fingers, etc. Now, there's some important things we need to understand about people's expectations when it comes to controls. So, for example, people expect a relationship between the way in which you move a control and the thing that's being controlled. Let me see if it's better if I just explain it in an example. So, for example, if we have a control that we move up or push forward or pull, that often often indicates an on outcome. On the other hand, if we pull down or push something rearward, then that often indicates an off position, etc. Up and to the right or forward or clockwise usually refers to increasing, and those opposite things used typically refers to decreasing. The same thing here with right and left in control of a cursor, say. So we tend to have these kinds of relationships in our minds, and going against those things will cause all kinds of havoc for your users. Control travel refers to the distance a particular control moves before it's stopped. So you can think about that on your keyboard. You've probably typed on some of those old kind of mushy keyboards, and you type and you just feel like, wow, I really have to push down far in order for this, this letter F or this letter T or whatever to show up on the screen. That amount of movement is called the keyboard's travel. And all kinds of push buttons, for example, have something like travel, which is the distance that it is moved before it stops. So automobile brake pedals, for example, have longer travel than other things like a keyboard. And you could see why that would be. Keys are activated by your fingers, which have very great tactile perception, whereas your feet don't. You really aren't very good at detecting how far something is moved when you're pushing it with your legs. You're pushing it with much bigger, kind of grosser muscles than with your fingers. So what we're trying to do then is to match the physiological capabilities of the body part. If you're controlling something with your feet, for example, well then that is going to have a fairly long travel. If you're controlling something with your fingers, that's going to have a very short travel. So for example, on the right hand side you can just see a Da Vinci robot and a surgical robot. For something like that, where you're trying to do something that's really fine motor control, you may not want to basically have, well, actually in that case you might want to have lots of travel before a particular action is made. So for example, imagine you're trying to go a very, very small distance between one physiological structure and another, or one anatomical structure and another. You actually might want to have to move your fingers a fair amount before that actually happens. Control gain is another example of how devices work or how controls work. It really refers to the amount of control movement compared to the amount of system response. So for a computer mouse with a 1-to-1 gain, that means you would have to, if you move the mouse 1 inch, it would move 1 inch on your screen. And a high gain means the cursor moves less than the mouse, while a low gain means the cursor moves more than a mouse. So for example, in a 3-to-1 gain ratio, which would be considered high, the mouse would move 3 inches, or if you move the mouse 3 inches, the cursor would move only 1 inch. Similarly, for a 1-to-5 gain, the mouse moves 1 inch and the cursor moves 5 inches. So think about the first part here, the 3 or the 1, as the part that the control moves, and this other part, the 1 or the 5, as the amount that the cursor moves. And in fact, the interesting thing here is, I've always thought that this was fascinating, a very low ratio causes, you've probably done this at an arcade or something, and you have to go pick up a little toy and you're using this joystick. That thing has a typically low gain ratio, and that causes the claw to move a lot when you barely touch the joystick, which is why we rarely win that game. Okay, some other things about size. It's important to sort of support safe and effective use among users with the largest physiological characteristics. So lots of times when you're trying to determine how big should I make some particular control, you're often best designing for the largest finger or hand size, because it's easier for a small hand to use something that's bigger than it is for a big hand to use something that's smaller. So it's usually a lot easier for people with smaller physical features to interact with something that's larger. It's important when we recognize if we want to really control something that surface area is pretty darn critical. The surface area of a control can really be thought of as the target. If you have too little surface area, well, that creates a pretty small target. If you got too much surface area, well, that increases the likelihood that you'll accidentally actuate something. So there's a delicate balance there, but you can see on this right side here, this skirted kind of design, one of the things it's trying to do here is increase the amount of surface area you've got on this particular knob. Not only do you have surface area here on this kind of fluted edging here, but you also have surface area on this kind of skirted edging as well. I think it's important to remember that fine motor control tends to require a lot of concentration. So it's particularly difficult to identify the target when you're trying to dial something in, or the stopping point if you're trying to get things just right. And lots of times people are not going to have kind of the bandwidth if they're being stressed out at that time or when they're fatigued. So this design of the control is really important. You need to think about the kind of state in which people are going to be using that control when you're doing the design. It's helpful if finger-operated controls support multi-finger use. So there's a couple multi-finger uses we should describe here. Rotary controls that require fine motor control should permit the use of at least 3 fingers. And using 3 fingers to control that increases accuracy. So the common example of that is called the 3-jaw chuck grasp. You probably didn't know such a thing existed, but basically it's grabbing a knob with 3 fingers and being able to move it. And that gives us better control over really small components like knobs and levers and switches and things like that. Now an alternative is kind of a 2-finger grip. That uses the thumb and the index finger as kind of a pincer grasp, and that doesn't provide as much control during rotational movements. You can get more control with 3 fingers than you can with just the 2. It's also the case that a pincer grasp can be a bit challenging for older adults as well as anybody that has peripheral neuropathy. I would, in terms of just advice, I would consider using texture on your controls. For example, rotary knobs can be improved by adding what's called knurling. You can see that example of knurling here to the surface, which sort of increases control and reduces finger slipping. You also want to do things like avoid sharp edges on surfaces, because those, well, they can hurt. They can cut at times. When you're transporting something, they can break off, for example. And some examples for improving that kind of situation is to add sort of a radius or a chamfer to the outside of the control, as you can see here. So one of the things that controls need to provide is some kind of feedback about what's happening. And controls should incorporate one or more of these types of feedback, if at all possible. So in particular, from a perspective of redundancy, users tend to benefit from 2 or more forms of feedback at the same time. So often when you're moving something, you can see it moving and maybe you can hear a click, for example. That would be the auditory part. Typically, that feedback should be immediate. It should be provided through multiple modalities. That's similar to redundancy, actually, so that we're not kind of only hearing, for example, feedback while we're in a noisy environment. We need to feel the feedback too. Otherwise, we won't be able to hear it very well. And it should be clear and understandable. Here's an example. We have to make some important decisions about the actuation force. Basically, how much force do you need to give the control before it actuates, before it actually makes a difference. So the ideal situation is to kind of identify a force that's easy to achieve for most users, but not so easy that it becomes accidentally pushed or actuated. And you can do that by testing this with user groups or users from each group. But I think it's important to consider each group's capabilities, and in some cases, that might mean creating different lines of products with different force thresholds. So, for example, if you are designing for a group that tends to have peripheral neuropathy, then you might have to design a system that requires a little bit more force because people are going to not have as good of sense of touch and won't get as much feedback from it. On the right hand side, you can see actuation forces by body part and control type, and I think those are expressed in newtons, as you can see, but those are kind of good first approximations to use. Then you'll want to dial those in using real honest to goodness users. You also might wonder where to place these controls, and this comes back to some old rules of thumb that I tend to use. I'll use this time and time again, not only with control placement, but with display placement as well as other things. I usually start with understanding and placing the most important controls in the closest, basically closest to the user. Then I go and I include the most frequently used controls as second. And then I group things according to two components: similarity, so that controls with similar functions are placed close together, and co-occurrence, so that those things that are used in the same sequence or procedure are close together. So anytime I'm designing anything and I'm thinking about placement, I'm thinking about those really four factors: importance, frequency of use, and then grouping according to similarity and co-occurrence. So I hope that brief discussion of controls is helpful to you, and I'll look forward to talking with you in the next lecture.